That way I don't have so much of a heavy class load when I come back.
Yeah, that wouldn't have been fun.
No, he's like, I'd take it here. He's like, that semester looks not hard, but time consuming.
Yeah.
I said, all right.
Okay, so I think I started integrity recording, but I cannot find the little, see, look, it's all the way up here. It's never up there.
I was going to say, I don't see
Is it?
next fall.
Okay,
Oh,
so
see.
let's go ahead and do the where we're at, where we're headed. I should clip the mic on. I think that does help the online students a little bit. Okay. So we are just, like I said, winding down. April 11th, we're doing our second lecture on Chapter 8 today. I'm not sure I can see to do this. And so 8A, the lecture today will cover quite a bit because I want to make sure that we have time to do some practice problems on Thursday. Because the complexity comes more on Thursday. Today it's just understanding the basics of it. And then Thursday it gets into how do we use that information to be able to make good business decisions. And of course, from my perspective, if we get you the basics but you don't know how to use it, we've not accomplished much. Okay? And then we'll follow up, and next week we'll move into Chapter 9. And I think what I'll also do, I probably am either going to next Tuesday or I'll do a separate recording on Part D of the project so that it just kind of goes over what the expectations are for everybody. So you should expect that either next Tuesday in class or just a separate online recording of that, and I'll post that for everybody. Any questions about where we're at or where we're headed? Nope, everybody? All right. So our second lecture on Chapter 8, we're managing flow variability and safety capacity, right? And so basically, we're going to spend some time today talking about waiting time. Isn't that? So here's my pun for the day. I bet you can't wait for this lecture, right? So exciting. It is maybe not exciting, but it's certainly practical. So try to keep that in mind as we work our way through it. Just kind of a review of some of the terminology that we talked about last time. If you remember, we said that throughput for a service process is the minimum of either the rate that customers are arriving, right, or the processing rate. So it's whichever one of those is smaller, that's going to be your throughput, okay? And our R sub P, which is our service rate, our process capacity, is the maximum rate at which customers can be processed by all the servers in the pool. So we're looking at all the servers when we talk about the throughput of the process, okay? And the average inflow rate is, again, just arrivals per unit of time, so customers per time, okay? So in example 8.1, let me go ahead and read from the text. Example 8.1, just to kind of frame it up for us. So that's on page 194 of your text. And example 8.1, so we're going to be talking about Vancouver International Airport. They have a security checkpoint. And the passenger, they come in and they place their carry-on luggage on a moving belt, which can be scanned by an X-ray machine. Okay? So each passenger is considered a customer, and the X-ray scanner is our server in this process. Okay? And so suppose as before, a customer carries an average of 1.5 bags with them, and that the X-ray machine can scan 18 bags per minute. Okay, so the X-ray machine then can process about 12 passengers' bags per minute, and the average time to process a passenger is 1 every 12 minutes. Okay, or if we were going to convert that to seconds, it's each 5 seconds. So with one scanner, so our C is equal to 1, the total processing rate is also 12 per minute. Okay, so prior to rescheduling flights, right, it's estimated that the arrival of customers is 15 per minute, right? And so we're in trouble. You can see that already because we can only process 12 per minute and our arrival is 15 per minute. So the average inter-arrival time is 1 every 15 minutes, or excuse me, our average inter-arrival time is 1 customer over 15 or 1 every 4 seconds. So the passenger throughput rate is equal to the minimum of either our 15 or our 12, right? So either the minimum, if we go back to what we were looking at here, of our arrival rate or our processing rate. And our arrival rate is 15 and our processing rate is 12, okay? And so that being the case, we're in trouble. So what happens is this chart just shows us that, okay, I have my first customer arrive and it takes me this long to process. Here's when my second customer arrives, and so they have to wait until here and then I process them, right? My third customer arrives, they have to wait till here, right? And you can see each succeeding customer, that waiting time just gets longer and longer and longer. So we have what's called an unstable process, okay? And so that being said, right, we want to see if we can reschedule the flights and make a difference, okay? So when we reschedule the flights so that we have a better arrival rate, so we have 10 customers per minute, that means that our inner arrival rate is 1 minute for 10 customers, meaning every 6 seconds. So our processing rate is still 12 per minute. So then our passenger throughput rate is the minimum of either the arrival rate or the processing rate. Now it is the arrival rate, which is actually lower. So leads us to think we could have a stable process. So 10 people per minute. And so if we look at our safety capacity, which is something we talked about, that's the difference between our processing rate and our arrival rate. So 12 minus 10 is 2 people per minute is our safety capacity. And we can now, because we're in a stable process, our capacity utilization is going to be our arrival rate divided by our processing rate. So 10 divided by 12 is 83.33, okay, percent. In the previous example, I think I asked it at the bottom of the slide, but we said, well, what's that utilization? Well, the utilization would have been over 100%, right? Because we had 15 customers arriving per time frame divided by the 12 processing rate, so we were over 100%. So again, it's not a stable process when that happens, okay? And so then what it looks like is this kind of perfect world, right? I have a customer, they arrive, I serve them, the next customer comes. Bing, bang, boom, and there's no waiting time, right? Okay, what's wrong with that? Any ideas what's wrong with that picture? Why isn't that real?
People don't come one by one.
That's right. People don't come one by one. Okay, and so when we talk about waiting time, our issues are all about variability then. So first off, we have to make sure that our processing rate is faster than our arrival rate. And secondly, we have to understand the variability. And we talked about the variability last Thursday, and we said when we go to Walmart or where we have to pick a cash register, right? The variability that we intuitively look for is A, what is the server processing? What's that variability, right? And B, how long is the line, right? And so those two things apply whenever we're thinking about the variability of waiting time. It's got to have to do with how long does it take for processing, right? And what's the variation? So you have variation in your processing and you have variation in your customers, okay? And so we have to think about both of those things. So for a service process, if the inner arrival and processing times are constant, queues develop if and only if the arrival rate is greater than the processing rate, okay? Just common sense. The long-run stability of a service process requires that on average, the processing rate, or how fast we supply service, is high enough to be able to process all of the arrivals. And that's what we call the stability condition. And it's necessary for limiting delays in queues. And if it's not satisfied, delays in queues will grow to infinity, okay? So we have these performance measures, and so some of what we need to figure out is how are they related, okay? So we're used to Little's Law, which says inventory is equal to throughput times flow time, right? Well, now we can apply Little's Law to both the inflow and the processing. And we can say the inventory and inflow is equal to throughput times the average time of waiting time, okay? And the inventory of processing, right, is equal to the throughput times the average processing time. So it's just Little's Law broken into the waiting time and the processing time, right? And so our total is inventory is equal to throughput times flow time. So then when I think about utilization, right, utilization can be calculated as the inventory in process divided by the number of servers, or I can take the throughput of the process divided by the throughput of the entire process divided by the throughput, the processing rate. Okay, we'll do some examples, I think, as we go through, but it's about, when you get to this chapter, it's about understanding Little's Law and how you can kind of piece it apart and put it back together, because we can break it into the inventory component of it and the processing component of it, and those relationships still hold true in terms of inventory is equal to throughput times flow time, but we can look at just those individual components. And so I could, for example, calculate I sub I and I sub P, and then add those together, and that's going to give me inventory of the total process, right? And so again, it's that. So if I had total throughput, and I could calculate I sub I and I sub P, then I can get to total inventory of the entire process. And so it's just these algebraic kind of how do these things relate, okay? So in the absence of variability, we can eliminate any weighting by ensuring that the processing rate exceeds the arrival rate, okay? But then, as I like to say, however, in the real world, we have unpredictable or random variability that a service process experiences, and that's called stochastic variability. So stochastic is just like a $10 word for random, right? So I don't know, the first several times I read this in some articles I had for the PhD program, I had to keep going back and looking up what does stochastic mean. I tell you what, if you want to feel how much there is left to learn out there, go read some academic articles. And then I thought I was pretty verbal, and I went my first semester, I had to have the electronic dictionary next to me just as I would go through. I'd be like, what do they mean by that? Oh, okay, well, they mean random, right? I could say random variability and understand it, but stochastic variability, right? But there's just hundreds of examples that are like that. Okay, so what happens when we add stochastic variability to our example from Vancouver Airport? Okay, well, now we don't have that very pretty picture, right? So we have one customer, and we see the processing rate for the first customer is longer, the processing rate for the second customer is shorter, then we have longer rate, and arrival rates are different times. And so then you can start to see we get, as time goes on, right, again, our customers have to start waiting longer because that variability is starting to stack on itself, and it's not working out like what we think it should, okay? So note, while passengers 1, 2, 3, and 5 don't have to wait at all, others do. So compared with example 8.1, where the inter-arrival and service times were exactly 6 seconds and 5 seconds respectively, where we were able to match the average of those examples, there was no waiting. We conclude that variability in these times leads to waiting in queues, right? So again, variability is kind of our enemy in service processing. Okay, let's just take a minute to fan ourselves and cool down. All right, so the effect of variability on process performance then is that it leads to delays, okay, in both queues and in service processing time. So even under the stability condition, meaning that our processing rate is faster than our arrival rate, variability leads to these longer lead times and customer delays, okay? So some customers have short inter-arrival times while others have long inter-arrival times. Some customers have short processing times while others have long processing times. Okay, so when these short inter-arrival times, meaning customers are coming rapidly, land with long processing times, right, that's going to have an effect on our line length or our queue. Okay, and queues then build up because that variability in processing time is independent of the variability of inter-arrival times. So those two things, the variabilities, are separate from each other. Just because you have long lead times, you can't make just because you have long processing times, it has no relationship to the rate at which your customers are going to arrive. Those two things are independent of each other. So suppose in our Vancouver International Airport, we were able to synchronize our short inter-arrival times of customers with short processing times, as well as our long inter-arrival times with their long processing times, right? Well, then it looks like that, right? Then we're able to make that work again, okay? So fundamentally, if you're able to figure out how to do that, right, then you're going to win in the length that your customers are going to have to wait. However, that's kind of hard to do. So back to the real world, right? So often we can't interchange processing times across customer arrivals over time and achieve that synchronization. So in 8.8, we study strategies for achieving some degree of synchronization, okay? So our key points up to this point in the chapter. If inter-arrival and processing times are constant, queues will build up if and only if the arrival rate is greater than the processing rate. Okay? If there is unsynchronized variability in inter-arrival times and processing times, queues will build up even if the average arrival rate is less than the average processing rate. And if variability in inter-arrival and processing times can be synchronized, right, queues and waiting times will be reduced. I'm going to try to open this door and see if that helps me. Actually, I'm just going to stand in the hallway and teach them out here. Oh my gosh.
I just need to bring a personal fan.
Well, yeah. Start bringing fans everywhere we go.
I know it. Okay, so our causes of delay. Okay, so this is maybe not an intuitive thing, because when we talk about capacity utilization, which is better, do you think, higher or lower? Which is better? What's that?
I feel like it's a trick question.
It is a trick question, because the answer is it depends. So it's that MBA answer, right? So that's what so when we're undergraduates, we always get these, it's either this way or it's this way, right? Well, now we're at that point where we're talking about it's a tool, right? And so what are you competing on? If you're competing on fast service, right, think about it this way. When you walk into the bank and your bank tellers are all busy, are you going to have to wait more or less? If your bank tellers are busy, are you going to have to wait in line longer or shorter? Longer, right? Because you walk in and they're busy. So they're highly utilized, but it means that you're going to have to wait longer. If you walk into the bank and they're not busy, right, meaning they have low utilization, then you don't have to wait very long. So what are you competing on? If you're competing on speed of process, right, you need to think about having a lower utilization rate for your servers so that your customers can get through the process faster. If you're competing on cost, right, and as a customer, I may be willing to wait in line longer because I know that it's a low-cost situation, right? That's how Disney gets away with their fast passes, right? You are willing to watch someone walk past you with a fast pass because you know that they paid more for that than what you did to stand in line. And that's your trade-off, right? You've made this mental, and they've done a lot of research to figure out what feels fair there so that they can charge that rate and people can walk by and it doesn't annoy all the other customers, right? And because you have a choice in that then. So again, think about that in terms of utilization. If service processes are highly utilized, then people have to wait longer, right? And if the utilization is lower, then they don't have to wait so long, okay? So high capacity utilization can come from a high inflow rate and a low processing rate, okay? High unsynchronized variability in inter-arrival times and processing times can also be a problem for us. So the key lesson from this first part of this lecture is variability matters, right? And so we try to find ways to manage variability in order to provide better service, okay? So again, our drivers of process performance that we're looking at here are both capacity utilization, right, and stochastic variability, right? So what's the utilization we have in the process and how random and what's the degree of variability that we see in terms of processing times and arrival times, okay? All right, and I say all that to get to the point that we're looking at, when we look at a waiting time formula to determine how long somebody's waiting in line, the most basic formula that we use is this. We look at these two factors, utilization and variability, okay? And we look at those factors because we look at the mean and variability of inter-arrival times and the mean and variability of processing times. And the reason that we do both the mean and the variability, right, is because if you think about it, if, let's say that, let me think about my example here. Let's say that you have your variability around the mean might be 1 minute, right? Okay? But if your mean is 1 minute, right, that's kind of a big deal. But if your mean is 20 minutes, 1 minute variability isn't as big of a deal. So you have to look at both kind of what I would say is the average and the range around that average. So we need to look at the mean and the variability to understand the degree of impact that that's going to have on the process. Okay? So we need to measure variability then in time relative to its mean. Okay? So we do that by using the coefficient of inter-arrival time and the coefficient of processing time. Okay? So when we talk about these coefficients, they're the ratio of the standard deviation to the mean. So that's giving us that comparison of what degree of variability do we have around the mean. I'm using the standard deviation and the mean. And so these measures are used to calculate queue length. Okay? So here's our formula that we start out with in Chapter 8 to calculate queue length. Okay? And we use it, if you look, when we talk about the amount of inventory that is going to be in the queue. So when we talk about queue length, that's what we're saying, is how many people are waiting there. Okay? We have the two kind of terms, and the one on the left side is for utilization, right? So I'm going to take the utilization rate to the square root of 2 times the number of servers plus 1 divided by 1 minus the utilization rate, and that gives us the utilization effect. Now, I could spend a lot of time proving that to show you how they got there, but I'm really good with just going, that's what it is, right? That's the utilization rate. Okay? Same thing on the variability effect. We're using those coefficients of inter-arrival times and the coefficient of processing times, and then we're basically taking the average of those two variability measures in our queue length formula. Okay? So where U is represented by the throughput of our customers arriving divided by the throughput of our processing rate, right? And where R sub P is equal to the number of servers that we have divided by T sub P, okay? So, and again, the C sub I and C sub P are those coefficients of variation that we're talking about.
So it's the utilization effect times the whole
Right. So
thing.
basically when I do this, I do I do parentheses here and parentheses here and solve each term individually and then multiply them together. And actually when I do it in Excel, I even break it. I do the numerator, I do the denominator, then I do the total, because it can get to be so many darn parentheses going on that it's easy to make a mistake that way. Okay? But basically, visually what we're saying is that as that utilization rate increases, so this is what we're talking about with those bank tellers being busy, right? The more busy they are, right, and the more variability we have, so there's this kind of relationship between utilization and variability, right, the longer we have to wait, right? And so that's what we're looking at here. This one, we're having increased utilization with lower variability. Increased utilization where our variability is increasing in terms of our arrival times and our processing rates. And then here we're just showing the highest level of that in this diagram. And so that's all they're trying to do is visually show you how your waiting time increases as your utilization increases and as your variability increases. Okay. So I'm going to go ahead, we're going to take a look at example 8.4 in the textbook. And I think that the easiest way to do this is going to be for me to read it to you and then walk you through how I did it in Excel. And because I think that trying to write it up on the overhead, it's not as clean as how it is in Excel, and I've got it set up in Excel so I can show you visually where things are done and how they're done. But 8.4 says, suppose, as an example 8.2 and 8.3, we observe the inter-arrival times of 10 passengers to be, and then they give us these inter-arrival times of these passengers. Okay? And I think what I'm going to do is go ahead and bring up that Excel spreadsheet. And I'll just show you where I have that information. And I put this spreadsheet on Canvas, so it's out there for you to review as you're doing your homework, because you'll have a homework problem that's similar to this. Okay, so basically what I'm showing here is in the problem, it gives us these 10 passengers, right? And it gives us the inter-arrival time of these 10 passengers, all right? So passenger 1, there is no inter-arrival time. They're just the first to arrive. But it's 10 seconds when passenger 2 arrives, then passenger 3 arrives 10 seconds later, passenger 4 2 seconds later, right? And so I'm just capturing that information. And in that same way, right, then we're given the processing time of those 10 passengers. Well, each of those has their own processing time. It took 7 seconds for passenger 1, 1 second for passenger 2, right, and on down. Okay, so all I've done is just capture the information of the problem in that yellow portion. Okay. The average inter-arrival time is then 6 seconds. Okay, so here's the average inter-arrival time. And what I've done is I've just taken the average of those 9 times. Okay, the confusing part to students sometimes is you want to take it time. There's 10 passengers, so you think, well, I should divide the total by 10. But we only have 9 inter-arrival times, 9 times between those 10 customers. Okay, and I can calculate my average processing time by, again, taking the average of those 10 times, right? So I'm starting to get that information I need for that formula, right? From my Q-length formula, I now have the average inter-arrival time, and I have the average processing time, okay? So then if I kind of keep moving, I can say, well, I need to understand the throughput, right? The inter-arrival rate, okay? It is the inverse of our inter-arrival time. So it's 1 over 6, which gives me 0.1667, and I r sub p for one server, and that's the inverse of the processing time, right? So it's 1 divided by 5, okay? And then to continue capturing information for that inventory formula, right? So I'm going to have to know, so we knew that I knew I needed r sub I and r sub p, right? And then other pieces of information that I'm going to need are going to be the coefficient of arrival time and the coefficient of processing time. And we said that coefficient is the standard deviation of the process divided by the mean. So I have to get the standard deviation of that process. So I take those 9 numbers and I use Excel to give me the standard deviation of those 9 numbers. And then that same way, I take those 10 numbers for processing rate and I get the standard deviation. Okay? And so at the end of the day, then I'm able to calculate the coefficient of arrival time by taking the standard deviation of those inter-arrival times and dividing it by the average. And that gives me the coefficient of inter-arrival time of 0.6562, right? And the coefficient of standard deviation of processing time is that same thing. I'm going to take the standard deviation that I calculated and divide it by the mean. So you can see it's just a matter of figuring out those variables in this equation and how do I calculate them and how do I get that from this information that I've got. Okay? So then we know that R is equal to the throughput of the process, right? And that's got to be the minimum of the inter-arrival rate of the processing rate. And the utilization of the process is R divided by R. Okay? So to estimate the average number of passengers in queue with one server, I thought, wow, there we go. We were missing that column. That's why that was not making sense. So our throughput then is the minimum of 0.1667 or 0.2, right? And again, we calculated that information up here. We're just coming back and pulling it together. And so our throughput of the process is 0.1667. And our utilization then is the throughput divided by the throughput processing rate. So 0.1667 divided by 2 gives us 83.3%. Right? Now I have all the variables I need to actually do this formula. And Julie, this is where you see I do numerator of term 1, right, is equal to u to the square root of 2 times c plus 1. So in our case with one server, we're dealing with the square root of 2, right, to the square root 2 times 2, right? So 2, we have one server, 2 times 2 here. I feel like you're not following, so I want to make sure you're seeing. I'm just dealing with this piece of it right now. So the square root of 2 times 2, so the square root of 4 is 2. So it's going to be utilization squared. So 0.833 squared is 0.6949. So that's my numerator for this term. Okay, my denominator is 1 minus my utilization rate. So 1 minus 0.833 gives me 0.1667. So that's the denominator. So the term 1 is the numerator divided by the denominator. Okay, so term 1 is 4.1655. Okay, and then over here I'm dealing with term 2, which is the coefficient of inter-arrival time squared plus the coefficient of processing time squared divided by 2. So that is, then if I come back and look, right, 0.6562 squared, 0.5657 squared, right, giving me my numerator divided by 2 gives me term 2. Okay, and at the end of the day, I take term 1 times term 2, telling me that my Q length is 1.5633. And we do this because I want you to appreciate when we get to the third part, how amazing the spreadsheet that we're going to use is. Okay, so you'll need to walk through this manually. It's twofold. I want you to appreciate the manual part of it, and then I want you to understand where the components are coming from, right? And so I think doing a problem like that is going to help drive home what the coefficient of inter-arrival rate is, what the coefficient of processing rate is, how you use the standard deviation to calculate it. I just want you to do at least one problem where you go through that process manually. And again, it gets more interesting because that formula works well when you have a limited number of servers. Okay. All right. So let's keep kind of. Let me see what. Okay, so we walked through all of that in Excel. And we could redo that with 2 servers, but I feel like that's kind of, that's overkill, right? All we're doing is changing the number of the C to 2 and calculating that. And so, I think what I'm going to do is go ahead and move on to the 3rd lecture, and that will give us time on Thursday to review more problems, and those problems on Thursday are going to be more value added just because we're getting to the meat of what happens. So let me go ahead and flip open to that lecture. So what happens is when we deal with that that equation that we just looked at, right? It's an approximation, okay? And so what we try to do is, of course, in statistical work, we try to get closer to reality every time, okay? And what we're doing is we're just kind of taking some estimations based on those coefficients of inter-arrival time and processing time. What the spreadsheet that we're going to use for this lecture 3 and kind of to do some of these last problems for the chapter does is it says that it really looks at that independence of the arrival time and the processing time, and it statistically calculates different options in terms of, okay, if this is happening independently and this is happening independently, what happens, okay? And we use what's called a Poisson approach. Okay, so we have this infinite pool of potential arrivals who arrive completely randomly and independently of one another at an average rate of that inflow rate. Okay, and it's constant over time. Okay, and we have this exponential processing time, which again is completely random and unpredictable during processing, and the time remaining does not depend on the time elapsed. Okay, so I can't tell you anything, if you two are standing in line, I can't tell you anything about how long it's going to take to process Austin based on how long it took to process Troy. Those two don't have anything to do with each other, right? And so in this exponential model, right, we're really taking that into account, okay? And so in an exponential distribution, the mean and the standard deviation are the same, so the coefficient of arrival time and the coefficient of processing time equals 1. So with this exponential model, we can do these computations where if the coefficients are equal to 1, then simplifies things when we have more than 2 servers, okay? And and it allows us to look at 2 types of models, okay? One of them meaning, which was all we looked at with the first formula, was an infinite model that said, it doesn't matter how many people get in line. We have an infinite capacity, okay? And so that's going to be something that you're going to need to hang on to in terms of understanding the difference between an infinite and a finite model, because you have 2 different spreadsheets that we'll use for that. Infinite says, I can have people get in line for days, and they can just be out there, right? Finite says, think of like the McDonald's drive-through, right? There's a limit before people are out on 641, and so you would say they only have a capacity for maybe 20 cars at a time, right? And so that would, you'd have to use the finite spreadsheet, okay? So that being said, here's how that same problem that we just looked at with the utilization rate of 83.3% shakes out with our inner arrival time of 6 seconds. So our average arrival rate is 10 per minute, and our average processing time is 5 seconds, gives us this 83.3%, or excuse me, it's the 0.833 minutes, but again, we have the 83.3% utilization, right? And if we were going to do that same thing with the 2 servers, which is the second tab of that spreadsheet that I showed you, we would come up with a utilization rate. Our utilization rate goes to 41.7, right? Our safety capacity goes from 0.033 to 0.233. The inventory of people waiting in line goes from 4.162 down to 0.175. The average time that they're waiting goes from 0.416 to 0.018. The average T, so do you notice that when I say T sub I read that as the average time that they're waiting. When I see T without any subscript, that's just the total time that they're in the process, 0.499 versus 0.101, right? And total number of people waiting, I, so again, I've got I sub I is the people waiting, and I'm sorry, the I without any subscript is the total number of people in the entire process, okay? So if I look at that, just to kind of make that relationship, I said that I've got 4.995 people waiting in the entire process, okay? And I have 4.162 people waiting to be served. How many people are in service? How would I get that? What's the relationship between those variables? So I have my total inventory with 1 server is 4.995, and I have 4.162 people waiting. How do I calculate how many people are actually in process?
I with nothing minus the inventory. I sub I.
You got it, right? So it's just that relationship of my total inventory is equal to the amount of people that are waiting to be served and the amount of people that are being served. So if I have 2 of those, I can get to the third, right? Okay, so sorry, I went the wrong direction. So capacity utilization and safety capacity, we're working with our demand management or our arrival rate at our, and we can increase capacity or the processing rate. Okay, so the number of servers is equal to the scale, and the processing rate is equal to the speed. Okay, I can think about variability reduction. Again, we talked about what are the things that are going to influence how long people wait in line. Is there a way to reduce the variability around scheduling, reservations, appointments? Is there a way to reduce the variability around processing times? Can I get standardization? Can I get specialization? Right? Maybe if I have a process that's complex, I divide my lines into 2 groups, right? One that's very straightforward and goes ching, 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 and goes through quickly, and another one that's over here that's more complicated, right? And so, but then maybe I have specialized training for the servers on that line, right? So they're actually able to, you're taking advantage of the fact that you've given this training, right? And they're focused on the customers who need that training. Instead of trying to broadly apply it, right, you're trying to be kind of more pinpoint precision. Okay? Or is there a way to synchronize and match capacity with demand? Right? One of my favorite examples of that, because the first time that I heard about this, nobody was doing it, right? And so, but what they're doing now is, at cities that have congestion problems and they have toll roads, right? The tolls are more expensive during peak traffic times of the day, trying to encourage people to go earlier or go later to reduce that, so again, matching capacity with demand, okay? All right. So when we have a finite system, right, K represents what's our buffer, okay? And so when you think about that buffer, it's the number of lines. Let's think of it in terms of telephone lines right now, because that's kind of an easy visualization for us. So that visualization says that if I have 5 telephone lines and I have 1 server, my buffer is 4, right? So K is going to be equal to the number of lines that you have minus however many servers you have. So if I have, let's say I have 5 lines and now I have 3 servers, my buffer is only 2 because I have 3 that are actually being served and then I have 2 that are waiting to be served, okay? And then I sub I represents that inventory and waiting. T sub I represents how long that they're going to be in waiting. P sub B, which is a new term for you, is going to be the probability of them being blocked from service. So if I have a finite system and I only have 5 lines, what's the probability that somebody's going to call in and can't even get in because those lines are full, right? So that's something that I think is a very useful measurement, because without this type of calculation, how would you ever even know who couldn't get into the system, right? And then R is our throughput of the entire system, right? And we could, again, it's going to be the minimum of the arrival rate or the processing rate, and then Q is our utilization, okay?
What was P sub B, probability of them being
Blocked.
turned away?
Blocked. Mm-hmm. Probability of blocking so that they can't even get into the service, okay? All right.
Inventory while they're waiting.
So the economics of capacity decisions, and this is where we're going to use this spreadsheet that we've got to start to calculate some costs, okay? So if we lose business, we lose so much per customer, and it increases with our competition. So the higher the competition we have, the more. So if I'm a monopoly and I don't serve you, you have to come back to me tomorrow, right? But if I'm not a monopoly and there's 100 other businesses out there that do the same thing, if you can't get into my business, you're just going someplace else, okay? Right? Then there's a cost of buffer capacity, right? How much does it cost to have that extra capacity? So it's dollars per unit of time. There's a cost of waiting, okay? And I'm more concerned probably about in the bolded black, and then we'll apply how we're going to calculate those. But that again is if I have to, I think in the maybe the introductory example, or at least as we go through that text, I want to say Land's End. Is that what it was? LL Bean. Okay, so it was the LL Bean example. So if I have a lot of buffer capacity and I only have 2 servers and I have 10 lines, that means that you're going to have to wait to get through 8 of those lines possibly to get served, right? And there's a number of people who are going to leave if they have to wait that long, and then there's a number of people who are going to buy less if they have to wait that long. So they can, statistically they can analyze based on how long a customer has to wait, what's the average rate of purchase. And what you can see is the longer they have to wait, the more that goes down. So you can apply a dollar value to that, right? We can get that based off of information in the system. Okay, and then we also have, we can't forget, we have a cost of processing. So it's not free to add another server, right? If I've got somebody else that's going to serve, well, that might bring down the waiting time, right? The actual cost of processing is going to go up. So all of these are going to be trade-offs, right? We have to try to find that sweet spot that says, how do we come up with the best approach in terms of cost and profitability, okay? And so our trade-offs then say that we need to consciously select how many servers are we going to have, what's that average time to process going to be, and how many buffers are we going to have. And so we want to minimize this total cost of this we've talked about all those variables, right? But now they're all in one glorious equation, right? And this is why I love to use Excel, because once you set it up in Excel, right, then it's a matter of just revising the information, and it's going to do the work for you. But you have to walk through it and get it set up for the first time. I want to stop there because I think that's enough conceptually for you to just kind of be aware of. And I don't want to start on any of these problems until next Thursday, but that's where we're headed. We're going to do the one kind of manual approach to just calculating inventory to make sure that we have that good understanding of how variability affects it and how utilization affects it. And then we're going to come back and we're going to work on this spreadsheet. And I think the spreadsheet is super cool. So basically we get to decide whether or not it's an infinite or finite system, input information, and it spits back almost all of those variables to you, and then you just have to plug them into the equation. So this manual calculation, you just have to understand how many servers you have, whether it's infinite or finite, what's the arrival rate and what's the processing rate, and then it goes poof, and there you go. You can do your trade-off calculations from there. So, all right, so that's my geekiness for the day, right? So thanks for your patience for the lecture on waiting time, right? So I'll see you back here on Thursday if I don't see you before then.